Hi everyone! In today's video we're going to talk about specific heat. So this is the energy of matter. Now specific heat is a property of substances and compounds. And off to the right we have a nice view of a beach with some water. And water actually has a high specific heat. And because water has a high specific heat, it can keep temperatures more moderate in summer and winter. So we'll talk a little bit about what specific heat is and how that works. All right, so let's define specific heat. And we sometimes abbreviate this as SH. So specific heat is different for different substances, kind of similar to density, depends on the substance that you're talking about. And specific heat is the amount of heat that raises the temperature of exactly 1 gram of a substance by exactly 1 degree Celsius. So, for instance, if we had 1 gram of water sitting in a cup, and we wanted to raise the temperature of the water 1 degree Celsius, how much energy would that take? How much heat would that be? So that's the specific heat. And again, this will be different for different substances. So the units of specific heat are joules per gram degree Celsius. So this is for the SI system. Now we can also use calories per gram degree Celsius, and that's more so used in the metric system. All right, so down below we have this written out as more of an equation. So specific heat is equal to the amount of heat that is needed over the mass of the substance in grams times the change in temperature. So we can write that as calories or joules per gram times degrees Celsius. All right, now down below that we have the specific heat values for water. So if we have 1 gram of water sitting in our cup and we want to increase its temperature by 1 degree Celsius, that would require either 1 calorie of energy or 4.184 joules of energy. So what we can say is that 1 calorie of energy is equal to 4.184 joules of energy. And this would be in the form of heat. All right, so you might be wondering if calories is the same as the calories that you see on your food labels or nutrition facts. And it sort of is, it's related. So the calories that you see on like your cereal box, that's a capital C calories. So 1 capital C calorie is equal to 1,000 lowercase c calories. Or we could also say it's equal to 1 kilocalorie. All right, so capital C calories that you see on your food labels, that is equal to 1 kilocalorie, lowercase c. So it gets a little confusing sometimes talking about that, but food does give you energy, and the calories that are listed there kind of tells you how much energy your food has, per serving, of course. All right. So I mentioned that different substances will have different specific heat values. So for instance, if we look at some elements, and I believe all of these are metals, their specific heats are pretty small. So we can look at either calories or joules, but they're relatively small. And then if we look at the specific heat values for different compounds like water or table salt or ammonia, which is in cleaning products, you'll notice that those values are a little bit higher. Now, what does that mean? So if you have a higher specific heat, that means it takes more energy to heat up that substance. Okay, so if you have a higher specific heat, that means that the substance requires more energy to increase its temperature, but it can also retain heat better. So requires more energy to increase its temperature, but also can retain heat better. And then the opposite is true. So if you have a lower specific heat, then less energy is required to increase the temperature of that substance, and that substance can release heat faster. So if looking at the metals here, remember last time we talked about copper and how copper has high conductivity. It's really good as cookware, so it can heat up your food really well. And that's because it doesn't take a lot of heat for copper to increase its temperature. But then additionally, copper can give off heat really easily, so it can heat up your food really easily. And that's true for most metals. Most metals have really low specific heats, so they can transmit heat really easily. Whereas other substances like water, they retain heat and they require a lot of heat in order to increase their temperatures. Now, that does come in handy. So if you are interested in nuclear reactors, water is used to cool down the nuclear reactors because water can hold on to a lot of heat. And then you can move that hot water somewhere else and bring in more cold water, and that keeps nuclear reactors from overheating. So we can use the specific heat of different elements and compounds to our advantage. Okay, so let's do a learning check. 1, when ocean water cools the surrounding air, A, cools, B, warms, or C, stays the same. Okay, so let's draw a little picture. Let's say we're at the beach and we're next to the ocean. I'll draw a little palm tree here. So let's say that the ocean is cooling off. So that means it's releasing heat. So this is the heat that's being released. So would the surrounding air also cool? Would it warm up? Or would the temperature of the surrounding air stay the same? It would warm up, right? So if the ocean's releasing heat, it's cooling down, then that means that heat is going into the air surrounding the ocean. So the air is going to warm up. All right, so now 2, sand in the desert is hot in the day and cool at night. Sand must have a high specific heat or B, a low specific heat. So remember, let's think about what high specific heat versus low specific heat means. High specific heat means that a substance retains heat well, and a low specific heat means that a substance transmits or releases heat well. So if sand is super hot during the day and then super cold at night, does sand have a high specific heat or a low specific heat? A low specific heat. So the sand can absorb energy really well and then transmit it really well at the same time. So sand can get super hot during the day and then super cold at night. Now, if we were talking about water, that would be different. So water can absorb a lot of heat and retain it. So water will maintain more of a consistent temperature. All right, so now let's talk about calculations using specific heat. When we know the specific heat of a substance, we can calculate the heat lost or gained by measuring its mass and temperature change. So let's look at our equation for heat below. So if we want to calculate the heat lost or gained by a substance, we need the mass of the substance, the temperature change of the substance, and the specific heat value of the substance. So the mass we can measure using a balance. So we'll just write balance here. The temperature change we can monitor with a thermometer. And then specific heat we would look up in a table. Okay, so now remember there were two different units of energy that we saw, either calories or joules. So depending on what unit you're using for your specific heat, so let's say you look up a value in terms of calories per gram degree Celsius, then you're going to end up with units of calories because you'll notice grams cancel and degrees Celsius cancel. Now, you could also look up the specific heat value in terms of joules per gram degree Celsius, and you'll end up with a value of heat in joules, because again, grams will cancel and degrees Celsius will cancel. All right. Now, also notice that we can use symbols instead of words to represent this equation. So heat, we could say, is equal to m, which represents mass, and then delta T, where the delta means change. So let's write that off to the side. So delta T, change in temperature, and then SH for specific heat. So let's do a quick practice problem, kind of going through that calculation or that equation. So what is the specific heat if 24.8 grams of a metal absorbs 275 joules of energy and the temperature rises from 20.2 degrees Celsius to 24.5 degrees Celsius? Okay, that's a lot of information. So let's actually write out all of that info. All right, so we're given the mass, which is 24.8 grams. We're also given the amount of energy or heat that's absorbed by the metal. So that's 275 joules. And the temperature rises from 20.2 degrees Celsius. So let's say that that's our initial temperature. So I'll write T initial. So that's 20.2 degrees Celsius. And then our T final is 24.5 degrees Celsius. Okay, So now what we need to determine, so it asks what is the specific heat. So we want to figure out the specific heat. Okay, so our plan is probably to use that equation we just saw. So I'm going to write that in a different color here so we know what's what here. So we just said that heat is equal to mass times a change in temperature times specific heat. But we're trying to figure out the specific heat. So what you could do, there's a couple of different ways you could solve this. You could plug in everything you know and then solve for specific heat. Or you could rearrange the equation before you plug in all of your values. So either way is fine. All right, so I'm going to rearrange this equation. So what we'll do is divide both sides by mass and change in temperature. Okay, so then mass cancels, change in temperature cancels on the right-hand side. So the specific heat is equal to heat over mass and change in temperature. All right, so I'm going to rewrite that equation. Okay, so our plan is to use this equation here. Okay, so let's plug in everything we know into that equation. So we have our heat, which is 275 joules. And then we're going to divide that by the mass, which is 24.8 grams. And then we're going to multiply by the change in temperature. So the change in temperature is equal to T final minus T initial. All right, so we'll plug in our T final, which is 24.5 degrees Celsius, and we'll subtract our initial temperature, which is 20.2 degrees Celsius. Okay, so let's simplify this. So let's figure out our change in temperature. So I'm just going to rewrite the other two values. Okay, so I've got my calculator handy. So we've got 24.5 degrees Celsius minus 20.2. So I get a value of 4.3 degrees Celsius. Okay, so now that we've determined our change in temperature, we can calculate the specific heat. So I'm going to plug in all these values. So I've got 275 divided by, and in my calculator, I'm going to put parentheses around everything in the denominator so that my calculator doesn't assume I'm multiplying everything by 4.3 because I'm actually dividing by 4.3. Okay, so 275 divided by parentheses, 24.8 times 4.3, close parentheses. All right, so my calculator gives me a super long number. So I've got 2.57876, etc. But how many significant figures should I include in my answer? So how many sig figs does 275 have? 3. How many sig figs does 24.8 have? 3. And how many sig figs does 4.3 have? 2. So remember, when we're adding or subtracting, we care about the decimal place. So when we did that problem, we got 4.3, which ends in the tenths place. But when we're multiplying and dividing, we care about the sig figs. All right, so our temperature change actually only has 2 sig figs. So that's going to determine our final answer. So we want to chop off the rest of this number after the 5. But the first digit we're dropping is a 7. So that means we have to round. So our final answer is 2.6. And then what are the units here? So we've got joules over grams times degrees Celsius. All right, so that's our final answer. So that's our specific heat of this metal. Now let's go back and see if we can identify the metal based on the specific heat. Maybe it says in that table we saw. Let's see. Oh, nope, I don't see a metal with that specific heat listed, so we'd probably have to go find a bigger table. Okay. And then here are the solution slides if you need that later. And next time, we're going to talk about changes of state. So we just talked about specific heat, which is a property of substances. And we talked about how some substances can absorb energy really well and release it really well. Some substances can absorb energy and retain it really well. So what happens when we do add heat to a substance? It's going to change its state eventually. So we'll talk about that next time. I will see you then.